Hi, welcome back. So in the last video, we talked about quantum numbers, and in this video, we're going to talk about orbital diagrams and electron configurations. So this is just another way that we're giving the addresses of electrons. So rather than writing out long sets of quantum numbers like we just did in the last video, we generally communicate where the electrons in an atom are using orbital diagrams and/or electron configurations. So these are the two things and what they look like. All right. Sorry, I think I was having some technical issues with the mic. So orbital diagram is a depiction of the arrangement of electrons in an atom or ion using boxes to represent orbitals. So nitrogen in the 1s, so remember that's your principal quantum number, and then the L quantum number, which tells you the shape of the orbital. So for nitrogen, we would put an electron spin up, spin down, and then here's the 2s, and then these are the three 2p orbitals. And we're going to get into how to do those. And then electron configurations give the number and the letter designations for all the electrons. So you can see here, 1s2 is like this, 1s, 2 electrons. And then 2s2, because there are 2 electrons here, 2p3, because there are 3 electrons in the p orbitals there. So if you have your Chapter 7 handout in front of you, this is a question on there. So Aufbau is the building up principle. So it's a method of building electron configurations by adding one electron at a time as the atomic number increases. When you're adding electrons to an atom, electrons always go in lowest energy orbitals that are available, and a maximum of 2 electrons per orbital, like we talked about. We also have Hund's rule, which means every orbital in a subshell is singly occupied with 1 electron before any one orbital is doubly occupied. And all electrons in singly occupied orbitals have the same spin. So what that means is that if you're putting 3 electrons in the p orbitals, you put 1 in each orbital first before you buddy them up. Degenerate orbitals are orbitals of the same energy. So the 3 2p orbitals are identical in energy. And the lowest energy configuration maximizes the number of unpaired electrons. So these ones are unpaired electrons, and these ones are paired electrons. So the order that we fill the orbitals, this is as we're going distance from the nucleus, and energy is increasing as we go away from the nucleus. So first the 1s, then the 2s, 2p's, 3s, 3p, 4s, and then something weird happens here when we get into those transition metals, that we go from 4s to 3d. So they're very close in energy, and it just so happens you fill the 4s first, then the 3d. And so usually they're so close in energy that kind of once you fill them, then they contract in, and then they're at a lower energy or closer to the nucleus. It's pretty complicated. So just remember that 3d fills after 4s. Within a given shell, meaning the principal quantum number, the subshells fill in order of s, p, d, f. And 4s is filled before 3d. This is just another image so you can see the energy increasing. Orbital energy gets closer together as n increases. So remember when we're going from that principal quantum number 1 to 2 is kind of our biggest leap. So here's 1s, 2s, you see 2p, 3s, 3p, and then that 4s, 3d thing, 4p like this, and then they get pretty close in here. So some strange things happen sometimes up here. So we're going to fill every element when we're filling up the electrons. We'll fill in this exact same order. So we're going to start with orbital diagrams first, and then from there we'll go to electron configurations. And they're pretty similar, so hopefully it'll be easy to translate from one to the other. So the orbital diagram is the depiction of the arrangement of electrons in an atom or ion using boxes to represent orbitals. The up-down arrows indicate the electron with plus or minus spin, up-down. So that m sub s quantum number that's either minus a half or plus a half, that's what that arrow refers to. And typically we draw this kind of half arrow thing just because that's standard. All right, so if you have hydrogen, and remember hydrogen just has one electron in it, so it's going to go in the 1s orbital, and there's just one of them. Then if you go over to helium, it's still in that 1s. So let's take a look at the periodic table real quick. So we're going to, hydrogen here is a 1s, and then we go across here, so we're still in that first energy level, the n equals 1, but then there's going to be 2 electrons in there. So the 1 gives you the principal quantum number, and the s gives you the shape of the orbital or type of orbital. So now we're going to look at core electrons versus valence electrons. So those core electrons are the ones that are inside close to the core, and the valence electrons are the ones that are kind of outside. So if we look at lithium, so lithium is this next one over here. We're going to first fill the 1s with 2 electrons, and then we go to the 2s and put 1 electron there. We can also, we'll do this shorthand thing here, where we take the noble gas from the row before, place that there, and then write the 2s with this valence electron here. So in lithium, we have 1 valence electron and 2 core electrons. So valence electrons are the electrons found in the outermost shell, or the highest principal quantum number. They are responsible for the chemical behavior of elements. So the reason these families, as we discussed in the first week, if they're part of this family, they behave similarly to each other. And the reason is because they have the same number of valence electrons, and that's where the chemistry is happening. The core electrons are the innermost electrons in the atom. All electrons that are not in the valence, all the electrons that aren't in the valence shell are core electrons. And we can abbreviate orbital diagrams and electron configurations using the noble gas from the previous row, like we did up here. So let's do some examples. I think that'll make it more clear. So let's look at orbital diagrams for carbon and nitrogen. So carbon is right here and nitrogen is right here. So they're in the second row, and they're, remember, these are the p's. So it's going to end with 2 p's. So first we fill the 1s's with 2 electrons, 2s's with 2 electrons, and then carbon is going to be 1, 2 into the p's. So that's why we put 1, 2 electrons in the 2 p's. All right, so how many valence electrons does carbon have? So you look at that highest principal quantum number, which is 2, and this is also a 2, so we have to count up all those electrons. 1, 2, 3, 4. So it has 4 valence electrons. Now let's take a look at nitrogen. So nitrogen on the periodic table is 1 farther than carbon, so we're just going to add 1 more electron right here. And then we go, if we want to see how many valence electrons does nitrogen have, we look at principal quantum number 2 and say 1, 2, 3, 4, 5. So nitrogen has 5 valence electrons. Now being able to figure out the valence electrons is going to be really important for the next chapters 8 and 9, where we're going to start drawing Lewis structures. So make sure you can look at the element and figure out how many valence electrons it has. These are what orbital diagrams are going to look like from hydrogen to neon. So we always fill in 1s first, and then the 2s, and then the 2 p's, you can see. So right here at nitrogen, they're all unpaired, and then once you get more electrons, you start pairing them up until you get down to neon, where the 2 p's are completely full. And so remember, neon is a noble gas, and oops, sorry. And so it's not reactive because all those electrons are completely full. They're paired up with each other, so that's why it's not very reactive. All right, so I want you to take a second and see if you can draw an orbital diagram for bromine. So I think we should write it out both long ways and then short ways. So pause the video if you need to and work it out. All right, technical difficulties. Okay. Sorry, there's no way to pause the video. So, all right, so we're going to draw an orbital diagram for bromine. So you're always going to start, make sure you have that periodic table in front of yourself. So for bromine, you're always going to start with that 1s. And then you have the 2s. And then you're going to look at the 2p's. And there, remember from our quantum numbers, there are 3 2p electrons. And bromine, you can see, is in the 4th row, so we're just going to have to keep going. So then we have the 3s. Then the 3p's. Then after you go to the 3p's, you come down to the 4th row, and you're going to go into 4s. And there are 2 electrons there. And then what comes after 4s? Remember, this is when we get into the 3ds. And remember, there are 5 d orbitals. And then we go to 4p. So you'll see bromine is in the 4th row, and it's in that p region. So let me show you on the periodic table. So we're trying to get over here to bromine. So it is in that 4th row. So we fill the 4 s's, then these 3 d's, and then we get to the 4 p's. And there are 1, 2, 3, 4, 5 in those 4 p's. So we put 1, 2, 3, 4, 5. So let me see if I can shrink this. Yeah, here we go. So now you can see the whole answer for bromine. If we were going to do this in the shorthand, we would see which noble gas comes on the row before, and it's argon. So you could just write argon and then put the last bit there. So argon takes you up to here. So then you would just there's your 3 Ds, and then your 4 Ps are going to look the same. All right, so this is, you have bromine the long way written out here, and then you can have the shorthanded way written on the bottom. So those are 2 different ways that you can draw it out. Okay, so now I want you to pause the video again here and see if you can answer this question. Okay, so let's take a look at this one. We have the 1 S's, 2 S's, 2 P's, 3 S's, 3 P's, 4 S's, and then we have 5 into the 3 D's. So what you want to do is take a look at your periodic table right here. So we're 5 into the 3 D's. So you just go down here. These are your 3 D's, and you go 1, 2, 3, 4, 5. So you know you're at manganese. So those 3Ds are found in the fourth row, transition metals. There are 5 3D electrons, so you go to the 5th transition metal in the 4th period, and you'll find manganese. All right, so now I want you to practice. Pause it again here and draw the orbital diagram for aluminum. So here's your orbital diagram for aluminum. So the first thing you want to do is go in here, and you'll see that aluminum is over here. So you can see that's into your 3 S's and then your 3 P's, 1 into the 3 P's. So you fill up 1s with 2, 2s with 2, 2p with 6, 3s with 2, and then 1 into the 3p's. So that's your orbital diagram for aluminum. So then we can also use core notation, which is this shorthand way. So we just find the noble gas from the row before. So if we go back to our periodic table, you see aluminum is here. So if you go to the previous row, you can see neon is that noble gas. So you put neon in little square brackets. And then you write the valence electrons after that. So your 3s2 and your 3p1. Okay, so those were orbital diagrams. Now we're going to get onto electron configurations, and it's basically the same thing, that just instead of drawing boxes with 2 arrows, we just put this little number 2 here. So we just looked at nitrogen. This is number and letter designations for all electrons. So this is the principal quantum number. This is the shell, or the orbital that you're in. Sorry, subshell. And this is how many electrons are in it. So this means there are 2 electrons in the 1s, 2 electrons in the 2s, and 3 electrons in the 2p. So again, keep in mind the s orbitals are here, the d are here, p here, and f are here. This is just a little picture to help you figure out how to fill them. So 1s, 2s, 2p, 3s, here we go, 3p, 4s, 3d, like that. So if that's helpful, different people will find different images helpful. So figure out what works for you. All right, so here's a list of electron configurations from hydrogen to neon. So we had a slide previously, and these slides are posted if you want to look through them more slowly. That you can see how these electron configurations match up with the orbital diagrams. Okay, so let's do a practice problem and electron configuration for indium. So first you want to look on the periodic table and find indium, and you can find it right there. All right, so indium, it looks like, what row are we on here? Is in the 5th row of the P's. So you're going to go, why don't we just do core notation? So you would go krypton first. And then you're going to go the 5 S's. Here, let's track back so we look. So 4s, 3d, 4p, 5s, 4d, 5p, and then 6x, and then 4f, and then 5d. Okay, so in here we don't have to get into the F's. So we're just going to go 5s2, 4d10, and then 5p1. All right, so we had 5s2, four d10, and then 5p1, right? Yeah, so we went 5s2, 4d10, 5p1. Sorry, I'm having a hard time juggling screens. Okay, so now let's practice a couple more. So practice writing out the electron configurations for silicon and selenium. Then write them again using the abbreviated core notation. How many valence electrons are in each element? So go ahead and pause the video and try that out. So here's silicon, 1s2, 2s2, 2p6, 3s2, 3p2. And then for the core notation, you can just replace up to here with neon. And this has 4 valence electrons. So you go to the highest number, which is 3, for your principal quantum numbers, and count up all those electrons. 1, 2, 3, 4. Then for selenium, we're going all the way to 4p4. Hopefully you found that on the periodic table. And then you want to abbreviate it with the previous noble gas, which is argon. And then you still want to keep these 3d10 in here. But you want to go with the valence electrons are the ones that have the highest principal quantum number, so that's 4. So this is 2 plus 4, 6 valence electrons. So even though the 3d10 is between there, it's a 3, so it's not counted in those valence electrons. So now there are a couple anomalies in the electron configurations. Of course, there's always exceptions to the rules. So for chromium and copper, they do not follow the pattern. All right, so you can see that chromium is here and copper is here. So you would expect this to be 1, 2, 3, 4 in the Ds. So it should be 4s2 and then 3d4. But it turns out it's more energetically favorable to put 5 in the Ds and only 1 in the S's. And then for copper, it's the same thing. You would expect it to be 4s2, 3d9, but what happens is one of those electrons goes to completely fill the d orbitals because that creates a little bit more stability. So these anomalies arise from stability associated with half-filled and completely filled d subshells. So I do want you to know that chromium and copper have these anomalies. All right, so then we can also look at the formation of ions, and we can write electron configurations for ions. So this is the gain or loss of valence electrons to achieve stable electron configuration. So those cations, remember we at the very first or second week discussed that sodium forms a +1 because it loses an electron. And once it loses that one electron, then its electron configuration looks like neon, one of the noble gases, so it's more stable. Chlorine, which is almost all the way to the right of the periodic table, gains 1 electron to form a chloride ion. And so then it goes from 3s2, 3p5 to 3s2, 3p6. So then those electrons are full and it looks more like argon. So those ions form so that they look like noble gases, and that's why they lose or gain the number of electrons that they do. So then we have isoelectronic ions in atoms. So the main group elements form ions by gain-loss of electrons to obtain noble gas configuration. So magnesium is in our second row, so it loses 2 electrons, so it looks like argon. Oxygen gains 2 electrons, so it looks like neon. Isoelectronic describes atoms or ions having identical electron configurations. So all of these ions, sodium, magnesium, oxide, fluoride, and neon, all have the exact same electron configuration. Sorry. Potassium, chloride, calcium, argon, all have the same electron configuration. So everybody's trying to achieve that complete valence shell. All right, here are some cations of transition metals. When electrons are lost to make cations, they lose the electrons from the orbitals with the highest N value first. So imagine you write down the electron configuration for iron. So the last one you put in was that 3d6 electron, but the one you're going to take away when you're making an ion are these 4 S's. So you're going to take away both of those 4 s electrons to make iron 2+, so then it looks like this. And then if you're going to make iron 3+, you take away both of those s electrons plus one of the electrons, so then it looks like this. So you're always going to remove that highest n value electrons first. So I want you to also be able to write electron configurations for ions. So pause the video here and see if you can write these out. All right, so you can see for iodide here, we wrote the whole thing out. So let's look on the periodic table. Iodide is over here. And if you add 1 electron, then it's going to look like xenon. And it's going to go into these 5p6s. And then we're going to have this guy. So this is krypton 4d7. So see if you got those answers. And if you didn't, you can ask me questions about them. All right, so we're going to end this video there, and I want you to practice electron configurations and orbital diagrams and then answer the questions for them. And in the next video, the last video for Chapter 7, we're going to look at periodic trends of atomic radii and ionization energy.